Welcome to Unit 5 review. This unit will focus on kinetics, which is the study of rates of reaction.
Specifically, this unit will cover reaction rates, rate laws, concentration changes over time, elementary reactions, the collision model, reaction energy profiles, reaction mechanisms and their relationship to rate laws, the steady state approximation, multi-step reaction energy profiles, and catalysis.
Let's start out quite simply by discussing rates of reaction and some important terminology that will be required to understand this concept.
A rate is defined as the measure of how some property changes over time. Just the way that speed measures distance traveled per unit time, a rate of reaction measures the change in concentration per unit time. This means how much reactant is used up or how much product is produced per unit time, which is usually measured in seconds. Sometimes this is easy to measure, like if a product of a reaction in liquid solution is a gas, and we measure the changing pressure that the gas exerts. If a colorless solution generates a colored product, we can measure the change in color by measuring light absorption. But whatever the method may be, rates of reaction are always expressed the same way, and that is change in concentration over time. For this decomposition of hydrogen peroxide, we can calculate the final concentration minus the initial concentration, giving us the change in concentration, and divide by time 2 minus time 1, which is the change in time, to get this expression. This is the rate expression. Brackets signify concentration, and delta, which is the Greek letter that looks like a triangle, means change in. So change in concentration over change in time. If this refers to a reactant which has a decrease in concentration as it gets used up in the reaction, this will be negative. For a product that is forming, it will be positive. Beyond the values being positive or negative, we must also see how they obey stoichiometry. Here is the combustion of ammonia. Notice the 4 to 5 to 4 to 6 ratio of the stoichiometric coefficients. In order to relate these rates of decomposition and formation to one another, we have to assign coefficients to each rate expression that are the inverse of these. So for ammonia, we have 1/4. For oxygen, 1/5. For nitrogen monoxide, 1/4, and for water, 1/6. The reactants will show a negative coefficient since they are being used up, and the products will show a positive coefficient as they are forming. The rate at any particular instant is called an instantaneous rate, and the rate at the very beginning of the reaction is called the initial rate. Instantaneous rates can be approximated by either taking an average rate over a very short time period or by graphing rate data and examining the slope of the line that is tangent to the curve at any particular moment. The slope of that tangent line will be the instantaneous rate at that moment. The rate of a reaction can be influenced by many factors, most notably reactant concentration, but also temperature, surface area of reactant, and the presence of a catalyst, and we will elaborate on these factors shortly. We can describe the relationship between a reaction rate and the concentration of its reactants by using a rate law. A rate law will take this general form, where the rate will be equal to a rate constant, K, times the product of the molar concentrations of the reactants, each raised to a particular exponent. These exponents are almost always positive integers, though it is technically possible for them to be fractions or negative numbers, and they are not evident from looking at the stoichiometry of the reaction. Let us state that one more time for emphasis, as this is an extremely common error among students. The exponents that we see here in the rate law are not related to and not necessarily equivalent to the stoichiometric coefficients from a balanced equation. Instead, these exponents must be determined experimentally. The exponents in the rate law tell us something called the reaction order. For a reaction with two reactants, the rate law would look like this. If M is 1, we would say the reaction is first order with respect to A. If N is 1, it is first order with respect to B. If N is 2, it would be second order in B. If it was 0, we would say it was 0 order in B. The overall reaction order is simply the sum of the individual reaction orders. So if M and N are both 1, the overall reaction order is 2, since 1 plus 1 equals 2. Here are some examples of rate laws with the reaction orders listed. Let's make sure we can write these. Say we are examining the reaction of nitrogen dioxide and carbon monoxide to form nitrogen monoxide and carbon dioxide. If we acquire kinetic data and find that the reaction is second order in NO2 and zero order in CO, what will be the rate law for this reaction? Well, in the rate law, each concentration will be raised to a certain power equal to the reaction order for that reactant. So given the data we collected, the concentration of NO2 will be raised to the second power, and the concentration of CO will be raised to the zero power, which makes it equal to 1. It can therefore drop out of the rate law, and we will see that the rate law for this reaction will simply involve the NO2 concentration squared. Let's try one more. For this reaction, the rate law is as follows. What is the reaction order with respect to each reactant, and what is the overall reaction order? We can see from the exponents that this reaction is second order in NO because of the 2, and first order in H2 because if no exponent is listed, it's the same as an exponent of 1, and the reaction is therefore third order overall since 2 plus 1 equals 3. Again, these exponents must be determined experimentally, and a simple way to do this is by looking at initial rates data. In working with initial rates, we simply compare two sets of rate data that differ in the initial concentration of only one reactant. For example, look at the reaction of nitrogen monoxide and ozone. We know the reaction rate depends on concentration, and we can do many trials of this reaction with different initial rates. If we compare two trials where one initial concentration stays the same, but the other one changes, we can determine the reaction order with respect to that substance. Looking at this data, let's compare trials 1 and 2. They have the same NO concentration, but for trial 2, the ozone concentration doubles. As a result, the rate doubles, so we know the reaction must be first order with respect to ozone concentration. This means that the concentration and the rate increase proportionately. Now look at trials 3 and 4. For these, ozone concentration stays the same, but in trial 4, NO concentration doubles. As a result, the rate doubles, so the reaction is also first order with respect to NO. That means the rate law will look like this, with exponents of 1 and with an overall reaction order of 2. Let's try another one. Look at this reaction where NO reacts with chlorine. We collect the following rate data over 3 trials. Let's find the rate law based on this data, which we know will look like this. We just have to find the exponents. First compare trials 1 and 2. NO concentration stays the same, but chlorine concentration increases by 50%. That's right, we don't need things doubling conveniently. We can work with any proportion of change. To find out the exponent for chlorine in the rate law, let's simply place one rate law over another, filling in data from trial 2 on the top and trial 1 on the bottom. The first two terms will cancel. We simplify a little further, and we see that N must be equal to 1. This means the reaction is first order in chlorine. Now compare trials 1 and 3. Chlorine concentration stays the same, but NO concentration increases by 50%. Let's do the same thing we did for the first two trials. Place the rate law for trial 3 over the rate law for trial 1. Everything will simplify just like it did the first time, and we can solve for M, which must be 2. That means this will be the rate law, which makes the reaction third order overall. Note that although the orders for each reactant match the stoichiometric coefficients, this is simply a coincidence. We can even use the rate law and the initial rates data to calculate the rate constant K. We simply have to plug in data from any of these trials and solve for K. Let's arbitrarily use the data from trial 1, do the arithmetic, and we will get this value for K. Let's try just one more example. We want the rate law and rate constant that correspond to this set of initial rates data. From trials 1 and 3, we can see that as OCL minus doubles, the rate quadruples, indicating second order. And from trials 2 and 3, we can see that as I minus doubles, the rate doubles, indicating first order. So that means this will be the rate law, and plugging in data from any of the trials will give us this as the rate constant. There is also a graphical technique that is very useful in determining reaction order, and it involves integrated rate laws. With these, we can just let a reaction run and monitor the concentration over time, collecting data over the course of a reaction, and perform a different kind of analysis. This will involve mathematical equations that can relate the concentration of some reactant at any time t during the reaction. We will use different integrated rate laws depending on the overall reaction order, and identifying the one that fits the experimental data will corroborate a particular reaction order. First, let's examine the case with a reaction order of 0. This means that the rate does not depend on the concentration of the reactant, so the rate law will look like this. The integrated rate law will look like this, where the concentration of A at any time t equals negative kT plus the initial concentration. Now, if looking at a reaction order of 1, the rate law will look like this, and the integrated rate law will involve taking the natural log of these two concentration terms. And finally, for a reaction order of 2, the rate law looks like this, and now we take the inverse of each concentration term and flip the sign on the rate constant. Now, this may seem arbitrary at first glance, but these integrated rate laws are ideal for plotting data because they are all in y equals mx plus b format, which we may remember from algebra as the equation for a line. On the left side is a y term. This rate constant, whether positive or negative, serves as the slope, m. Time is our x term, and this last term acts as b, the y-intercept. The way this works is that if we choose the correct integrated rate law to do our graphical analysis, we will get a linear relationship between what's on the two axes. In other words, we will get a straight line. We can see that for a zero-order reaction, plotting concentration versus time gives us a straight line, and the slope is equal to the opposite of the rate constant. For a first-order reaction, plotting the natural log of concentration versus time gives us a straight line, again with the slope equal to the opposite of the rate constant. And for a second-order reaction, the inverse of concentration versus time gives us a straight line, where this time the slope is equivalent to the rate constant. So when we record kinetic data, instead of doing multiple trials to compare initial rates, we can try to plot kinetic data from one trial according to these different relationships, and the one that gives us a straight line will tell us the overall reaction order simply by graphical analysis. Before moving on, let's just say a few things about the rate constant. We should understand that the units on it will be specific to the overall reaction order. This is because they must cancel out the concentration units to give molarity per second, which are units that make sense for the rate. So for zero order, they will be molarity per second, since a zero order reaction doesn't depend on concentration. For first order, it's inverse seconds, so that when combined with molarity, we get molarity per second. For second order, it's 1 over molarity times seconds, so that when combined with molar squared, we get molarity per second. Looking at this particular reaction, the units on K must be 1 over molar squared times seconds, since there will be molar cubed in the numerator. Likewise, this means that if you know the rate constant, you must also know the overall reaction order. Just see how many powers of molarity have to be in the numerator to result in a rate of molarity per second.
With rate laws understood, let's now take a look at collision theory and reaction mechanisms, which describe chemical reactions on the molecular level.
If we want to understand a chemical reaction on the most fundamental level, we will have to learn about collision theory. This is a theory that describes collisions between molecules, which is what has to happen in order for a reaction to occur. The postulates of collision theory are as follows. 1. The rate of a reaction is proportional to the rate at which reactant molecules collide with one another. In other words, the rate is proportional to the number of collisions per unit time. 2. If two molecules are to react, they must collide with a particular orientation, namely so that the two atoms that are to form a new bond are specifically the ones that come in contact with one another. And 3. The collision must occur with enough energy so as to allow the reacting atoms to penetrate each other's valence shells and cause electrons to rearrange and form new bonds. Let's examine postulates 2 and 3 a bit further to enhance our understanding. Consider the reaction of carbon monoxide and oxygen to form carbon dioxide and an oxygen atom. In order to react, a molecule of carbon monoxide and a molecule of oxygen must collide with one another, but the oxygen molecule must specifically collide with the carbon atom, since the new bonds that are to be formed occur between the carbon and oxygen atom. If the oxygen molecule collides with the oxygen atom in carbon monoxide, no reaction will occur. This shows how the orientations of the reactant molecules makes a big difference. Then, beyond orientation, even if the oxygen molecule collides with the carbon atom on carbon monoxide, it must also do so with sufficient kinetic energy so as to overcome the activation energy of the reaction. This is the energy required to reach the transition state of the reaction, where bonds have partially formed and other bonds have partially dissipated, a point beyond which the reaction will certainly occur. The transition state is not something that can be captured or isolated. It only exists for an instant before the reaction proceeds to completion. But nevertheless, it is the energetic barrier that is placed on any reaction. And once again, the more collisions there are per unit time that do have the correct orientation and sufficient kinetic energy, the faster the reaction will go. We can look at a Maxwell-Boltzmann distribution curve to see the distribution of kinetic energies for particles in a sample, and this will allow us to estimate what proportion of them will have enough energy to surpass the activation energy, and this proportion will change as temperature changes. Specifically, at higher temperatures, the average kinetic energy of the particles increases, and more of them will therefore collide with enough kinetic energy so as to react successfully. Now let's relate this concept more broadly to chemical reactions. In learning about stoichiometry, we dealt with coefficients in a balanced chemical equation. But this balanced chemical equation doesn't really tell us what is happening on the molecular level. In order to talk about what individual molecules are doing over the course of a chemical reaction, we will have to discuss the reaction mechanism, which is the pathway by which a reaction occurs. Unbeknownst to the macroscopic observer that cannot see individual molecules, a reaction will often proceed over multiple steps. For example, the decomposition of ozone to become diatomic oxygen can be shown using this overall reaction, but in reality this reaction happens in two steps. First, a molecule of ozone will lose a singular oxygen atom to become diatomic oxygen, and then that lone oxygen atom will react with another molecule of ozone to generate two more molecules of diatomic oxygen. Each of these steps will be referred to as an elementary reaction. These occur exactly as written and cannot be broken down further into simpler steps. These elementary reactions add up to give the overall reaction, which in this case would show two ozone molecules yielding 3 molecules of diatomic oxygen. Once again, from the overall reaction, we can know all kinds of things about stoichiometry, but to know what is happening every step of the way, we must refer to the reaction mechanism, which is the series of elementary reactions. Looking again at the mechanism, we notice that monoatomic oxygen is present as a product in the first step and a reactant of the second step, but does not show up in the overall reaction. That means monoatomic oxygen is an intermediate in this reaction. Let's introduce another concept. The number of reactant species involved in each elementary reaction is called the molecularity of the reaction. Let's examine the different degrees of molecularity that are possible. Some reactions do not involve a collision. They simply involve the decomposition of a singular molecule. These are called unimolecular reactions. Here are some examples of these, like the decomposition of ozone and the decomposition of cyclobutane. Energy is required for any reaction to occur, even unimolecular reactions. So even though these do not involve a collision between two different molecules, the reactant must either be traveling with a kinetic energy that is greater than most of the other molecules in the sample, or it must collide with the edge of the container. For unimolecular reactions, the rate is proportional to the concentration, since the more molecules there are, the more of them that will have the energy sufficient for the decomposition to occur. Most often, reactions will involve two molecules that collide with one another, whether they are the same type of molecule or two different types of molecules. In either case, this will be called a bimolecular reaction. These types of reactions could either be first order in A and first order in B, or second order in A, depending on the identity of the molecules involved. Some transformations involve elementary steps that are bimolecular in nature, and some overall chemical reactions involve a single step that is bimolecular, like these two examples, one with two different molecules and one with two molecules of the same type. While bimolecular reactions are the most common, there are reactions that we would define as termolecular, meaning three different molecules must collide at the same time in order for the reaction to occur. This kind of reaction is uncommon because the probability of three specific molecules colliding simultaneously is much less than for two, by a factor of 1,000 in fact. Nevertheless, these types of reactions exist, such as the one where two molecules of nitrogen monoxide react with one molecule of oxygen to produce two molecules of nitrogen dioxide. We should also note that these elementary steps that make up the reaction mechanism will typically vary greatly in their rates, and there will usually be one elementary reaction that is the slowest by a significant factor. This is called the rate-determining step. This is the step that limits the rate at which the overall reaction can occur. What can the rate-determining step tell us about the rate law? Well, we know that the rate law for some chemical reaction, like this one here, cannot be found using the stoichiometry of the overall reaction. These exponents must be determined experimentally. But if we have the reaction mechanism, things are a little different. The exponents in the rate law can be determined by looking at the stoichiometry of the rate-determining step from the reaction mechanism. For example, when nitrogen dioxide and carbon monoxide react to form carbon dioxide and nitrogen monoxide, the rate law is found to be first order in each reactant when the temperature is above 225 degrees. However, at lower temperatures, the rate law shows a second-order reaction with respect to NO2 and zero order in CO. This is not consistent with a single-step bimolecular reaction, as is shown in the overall chemical equation. Instead, a mechanism like this makes more sense. As we can see, the first step is the rate-determining step, and the rate law we could derive from the stoichiometry of this elementary reaction will match the rate law for the overall reaction below a certain temperature. Whenever the rate-determining step is the first step in a reaction mechanism, the rate law for the overall reaction will simply be the rate law for this first step, and this will often be the case for multi-step reaction mechanisms. In the case where the rate-limiting step is not the first step, something called the steady-state approximation can be used to determine the rate law. This involves the assumption that the concentration of a reaction intermediate remains constant over the duration of a reaction, because the rate at which it is being produced by one elementary reaction is equivalent to the rate at which it is being consumed in another elementary reaction. So reaction mechanisms are useful not just to give us a clearer picture of what is happening on the molecular level, but also because a rate law can be derived directly from the stoichiometry of the rate-determining step without gathering any experimental kinetic data.
Reaction energy profiles, or energy diagrams, depict how potential energy changes over the course of a reaction, and these are important to be able to interpret, so let's go over these as well.
On an energy diagram, the horizontal axis is the reaction coordinate, or essentially just time, and the vertical axis is potential energy. Molecules are always reacting in such a way so as to allow the system to go lower in potential energy. So to put it simply, things want to go down. On the left, we have reactants. Then this hump represents the activation energy to get to the transition state, after which it comes back down to form the products. We will discuss enthalpy in more depth in the next unit, but to learn some basic terminology right now, if products sit higher than reactants, then energy must be absorbed to achieve the transformation, which makes this endothermic. If products sit lower than reactants, energy will be released as a result of this transformation, which makes this exothermic. The change in enthalpy is the distance between reactants and products, while the distance from reactants to the transition state is the activation energy. Some reactions are reversible, and the activation energy for the reverse reaction will be the distance from products to the transition state, as the products of the forward reaction are the reactants of the reverse reaction. We can construct such a diagram for a reaction with one step, or if we want to display an entire reaction mechanism, we can construct a multi-step reaction energy profile, where each peak represents a transition state and each valley represents an intermediate, so we can assign an activation energy to each step of the reaction, while the overall change in enthalpy is still the distance from reactants to products. To cover some more important terminology, we've probably all heard the word catalyst before and know of the common definition as being something that speeds up a process. But in chemistry, there is much more to discuss, as the more fundamental action of a catalyst is that it lowers the activation energy of a reaction. This is the cause of the faster rate, since more collisions per unit time will have sufficient kinetic energy to overcome this lower activation energy, and therefore result in a reaction. Beyond this, we must understand that the catalyst is not used up stoichiometrically in the reaction. This means it either is not consumed, or it is regenerated as the reaction proceeds, so that one molecule of catalyst can facilitate many chemical reactions. Some reactions that would normally have an activation energy too high for the reaction to proceed will proceed readily in the presence of a catalyst because the catalyst offers an alternate pathway. Whatever this alternate pathway that is provided by the catalyst may be, it could have just one step, like the uncatalyzed reaction, or it could be a multi-step pathway, as is shown here. But no matter what, the activation energy will be lower. Types of catalysis include acid-base catalysis, where proton transfer makes a reactant more reactive; surface catalysis, where the surface of a solid catalyst promotes some kind of reaction via the formation of intermediates that interact with the catalytic surface; as well as biological catalysis with enzymes, which form an enzyme-substrate complex where the enzyme interacts with the substrate, sometimes even covalently, to lower the activation energy of some biochemical reaction. Finally, we can combine our new understanding of collision theory with rates of reaction with something called the Arrhenius equation. This will relate the activation energy of a reaction to its rate constant. We can see that this reaction will also include the gas constant that we remember from our study of ideal gases, although this time we will more typically use a different version, 8.314 joules per mole Kelvin. In addition, we see the temperature of the reaction in Kelvin, while E is a number we may remember from math, and A is a constant called the frequency factor, which is related to the frequency of collisions and the orientation of the reacting molecules. What this essentially tells us is the fraction of molecules that will have sufficient kinetic energy to get over the activation energy of the reaction. As we noted earlier, this will certainly depend on temperature, and as we can see here on plots of the fractional distribution of molecules versus kinetic energy, as we raise the temperature, the whole distribution shifts right, which means more molecules will have more energy, and we can see that at the activation energy of the reaction, more molecules from T2 will have at least this much energy than molecules at T1, since T2 is greater than T1.
One more concept related to kinetics we must understand is that of half-life and nuclear decay. Let's make sure we understand the basics of these nuclear reactions as well.
When we talk about chemical reactions, we are talking about the rearrangement of atoms. Chemical bonds break and form to generate new substances, but each atom remains unchanged. However, there are reactions that involve the particles inside the nucleus, and the particles that a nucleus can emit or absorb, and these can, in fact, alter the identity of an atom. These are referred to as nuclear reactions. In order to depict nuclear reactions, we have to use nuclide symbols, which, as we recall, involve a chemical symbol and two numbers to the left, the lower of which is atomic number, or number of protons in the nucleus, and the upper of which is mass number, or the sum of the numbers of protons and neutrons in the nucleus. Atomic nuclei are extremely dense, much more dense than bulk matter, since the atoms that make up most of what we can see are predominantly empty space, while inside a nucleus, the nucleons are packed very tightly together. While the electromagnetic force dictates that the positively charged protons will be repelling each other, since like charges repel, it is the much stronger and aptly named strong nuclear force that attracts and binds all nucleons and makes the nucleus stable. However, some nuclei will be unstable. To understand why, we must examine the neutron-to-proton ratio for all of the stable isotopes that we know of. That's what this chart shows, with the number of neutrons on the vertical axis, the number of protons on the horizontal axis, and every stable isotope we know, like carbon-12 or oxygen-16, is represented by a dot on the chart. If this black line with a slope of 1 represents a precise 1-to-1 ratio of neutrons to protons, then we will define this region here as the band of stability, because it is a roughly linear region that contains all of the stable isotopes. It also reveals a firm preference exhibited by nature to use nuclei that at very low mass show roughly a 1-to-1 ratio, like nitrogen-14 with 7 protons and 7 neutrons. But as the nucleus gets larger, the ratio shifts closer to 1.5 to 1. This is because as more and more protons are added to the nucleus, the repulsion between them gets greater and greater, so more neutrons, which are of neutral charge, are needed to diffuse some of that repulsion. In addition to this preferred ratio, we can see that nature prefers to have both protons and neutrons present in even numbers, as 157 out of the total 265 have even numbers of both, and only 5 of these nuclei have odd numbers of both protons and neutrons. Apart from the electromagnetic force and the strong nuclear force, there is also the weak nuclear force, which mediates nuclear decay. This is important in the context of nuclear reactions, because if a nucleus is unstable, it will undergo some kind of nuclear reaction in an attempt to become more stable. This will typically involve emitting a particle of some kind, so let's go over these particles and their properties. The first is the alpha particle. When this particle was discovered, we did not know what it was, so it was simply named alpha, but we later found out that it is a helium nucleus, so we can refer to it with either the alpha symbol or the helium symbol. This has a mass of 4 atomic mass units, so the mass number will be 4, and since there are 2 protons, the atomic number will be 2. Next is the beta particle. These are high-energy electrons, and we can represent them with either an uppercase beta or an E for electrons. Note that the mass of the electron is negligible, so in the nuclide symbol we put a 0 for mass. However, we put a -1 for atomic number because it will cancel out a positive charge from a proton. Next is the positron. This particle is an example of antimatter, which is a concept that is so strange and tangential to our purposes here that it's best to completely avoid rigorously describing antimatter. We just need to know that the positron is the antimatter version of the electron, so it has the same mass as the electron, but is opposite in charge. For this reason, we assign it either an E or an uppercase beta, just like the electron, but we will assign it a +1 for the atomic number, as it is positively charged. Next, we have the proton and the neutron. These should be very familiar, as they are the normal nucleons found in any atom. A proton can be referred to with either a lowercase p or a capital H, as a hydrogen nucleus is simply a proton. This will have atomic number 1 and mass number 1. The neutron will be referred to with a lowercase n, and it will also have a mass number of 1, but its atomic number will be 0, as it has no charge. Lastly, there is the gamma ray. This is a photon of exceptionally high energy. This will be symbolized with a gamma and 2 zeros, as light has no mass. And so these particles, the alpha particle, beta particle, positron, proton, neutron, and gamma particle, are the ones that will be involved in the nuclear reactions we will be examining. Emission of any of these particles will happen for a very specific reason, so we will want to understand the cause of each in the context of a nuclear reaction. Perhaps the best way to understand these nuclear reactions is to learn how to balance them, so let's learn how to do that first. Take a look at this nuclear reaction. This says that polonium-212 becomes lead-208 when it emits an alpha particle. This is a valid nuclear reaction because it fulfills two important criteria. Number one, the mass numbers must add up to the same value on both sides of the equation. On the left we have 212, and on the right we have 208 plus 4, which equals 212. So the mass numbers are valid. Number two, the atomic numbers, which in a broader context we can think of as charges, given how we notate certain particles involved in these reactions, must add up to the same value on both sides of the equation. On the left, we have 84, and on the right, we have 82 plus 2, which equals 84. So the charges are also valid. This type of reaction will typically happen if the nuclide does not fit into the band of stability, often because the nucleus is simply too large to be stable, and the strong nuclear force dissipates more rapidly than the electromagnetic force, such that proton-proton repulsion starts to outweigh the force holding the nucleons together. Next, look at this reaction. This one says that when a nitrogen-14 is bombarded by an alpha particle, it produces oxygen-17 and a proton. Again, this is valid because the mass numbers add up to 18 on both sides, and the charges add up to 9 on both sides. Here we see that if beryllium-9 is bombarded by an alpha particle, we get carbon-12 and a neutron. Again, the mass numbers and charges check out. Additionally, looking at this reaction, we see that if a uranium-235 nucleus is bombarded by a single neutron, it will split up into a bromine-87 nucleus, a lanthanum-146 nucleus, and 3 other neutrons. Again, the masses and the charges are balanced. So remember that when writing nuclear reactions, we need both the mass numbers and charges to add up to the same value on both sides of the equation, just like these 4 examples. Let's try one example to make sure this makes sense. If magnesium-25 is bombarded by an alpha particle, it will produce a proton and some other nucleus X with mass A and charge Z. What must this nucleus be, considering what we know about balancing nuclear reactions? Well, let's take a look at the mass numbers. On the left, we have 25 and 4, which add up to 29. That means that on the right, 1 and A must also add up to 29. That makes A equal to 28. Then for the charges, on the left we have 12 and 2, which add up to 14. That means that on the right, 1 and Z must also add up to 14. That makes Z equal to 13. If this nucleus has an atomic number of 13, then by definition it is an aluminum nucleus, and so with a mass of 28, this particle must be aluminum-28. Again, these types of nuclear reactions will occur if a nucleus is unstable, either due to being too large or to having an unfavorable neutron-to-proton ratio. We can describe the time it takes for radioactive material to decay using a parameter called half-life. This is the amount of time that must elapse for a sample of radioactive nuclei to be reduced to half the original amount. For example, carbon-14 has a half-life of 5,730 years. So after one half-life has elapsed, half the original amount of carbon-14 will remain. After another half-life elapses, half of that amount, or 1/4 the original amount, will remain. With each half-life, the remaining amount is cut in half, so it is not the case that half of it decays and then the other half in one more half-life. It is a logarithmic relationship. To relate this parameter to our study of kinetics, the half-life for a first-order process will be equal to 0.693 over the rate constant. Notice that this will not depend on reaction concentration.
And that concludes our Unit 5 review on kinetics. So I'll see you over in Unit 6, where we will discuss thermodynamics.